Okay, let's work through these free response questions on our study guide. So the first free response question is related rates, and we're dealing with a perfectly cylindrical piece of pizza dough, because that's realistic, right? So what do we know? Let's see. It's a constant volume. That's important. And the other thing we're going to point out right away is the radius is increasing at a rate of 22 inches per minute. So right off the bat, I'm going to write down dr dt because that's going to come in handy. Okay, so part A, we have to find the rate at which the area of the surface of the dough is increasing with respect to time. Let's do that up here. So we're going to write out the area formula, pi r squared. And we're going to take the derivative of A with respect to time. 2 pi r, dr dt. Okay, so let's plug in r. We know r, it's 12. Let's plug in dr dt. So 2 pi times 12 times 22. 24 times 22. So for dA dt, we get 528 pi. And then our units would be inches squared per minute because area. Cool. That's part A. Easy enough. Part B. So for part B, we have to find the rate at which the height of the dough is increasing with respect to time. So we're going to find dH dt. Okay. So this time we're going to work with the volume formula for a cylinder. So pi r squared h. Let's take the derivative. So the derivative of volume is going to be dv dt. And we have two variables, which are both functions of time here. So we're going to have to use the product rule. Okay, so I'll do the h first. So pi r squared, derivative of h is just 1 dh dt. Plus, take the derivative of r, 2 pi r, leave the h, dr dt. A little gross, but it's not terrible. And we also know that v is constant. Therefore, the derivative of a constant is 0. So dv dt equals 0. So we're going to use that here. We're going to replace that with 0. And we need to solve for dH dt. So a little bit of algebra. I'll save you the time here. You can work out the steps on your own if you need to. So dH dt, if we solve for it, we should get negative 2 pi rh all over pi r squared dr dt. Do a little cancellation here. So we get the pi's cancel. We lose r on top. So we have negative 2h over r dr dt. If we plug all that in, let's see, negative 2, h in this case is 1/3. R is 12. dr dt is 22. So I punched all this in my calculator and I got negative 1.2 repeating inches per minute. And I said you guys could skip C, so don't worry about that. We'll come back to stuff like C later, but basically that's a parametric equations problem, which we're going to look at a lot later, so no big deal. Okay, moving on. FRQ2. We got some implicit differentiation to look at here. Let's see, part A. Here's our curve. We have to show that the derivative works out this way. So we're going to start with taking the derivative. So we got 2x plus 2 plus 4y cubed. And implicit, anytime we take the derivative of something that's not x, we need to put d, whatever that variable, dx, so dy dx, plus 4 dy dx equals 0. Nice, now we just need to solve. So let's move everything that's not a dy dx, and then we'll factor out. So quick little algebra here. Minus 2x minus 2. We can factor a negative 2 out of that, and we can divide by the 4y cubed plus 4. So we should get dy dx is equal to negative 2 times x plus 1 divided by, let's factor out a 4, y cubed plus 1, and one more step. Let's see, so that can go away. That becomes a 2. And hey, that's what we set out to prove, right? Mission accomplished. Cool, so that's part A. Part B. We need to write an equation for the line tangent to the curve at the point negative 2, 1. So we're going to use point slope, y minus y1 equals m x minus x1. So the point negative 2, 1, so our y1 is 1, our x1 is negative 2, and our slope is whatever we get when we plug that point into the derivative. So let's do that. So in a problem like this, your points, the points that you score on this problem are coming from showing that, hey, I need to plug this point into the derivative, actually doing it, and then writing out the equation. So let's plug this in. So we got, what, negative 2 plus 1. All over 2 times 1 cubed plus 1. If we simplify this out, we should get, let's see, negative 1. So 1, 2 times 2, 1 over 4. So there's our slope. So our tangent line equation should be, forgot the E. Y minus y1 equals m x minus x1. And that's it. Part B done. Part C, find coordinates where we have a vertical tangent. Okay. So you're going to have a vertical tangent wherever the slope is division by 0. So that's going to occur. So wherever the bottom of this fraction is 0, so wherever y cubed plus 1 equals 0. In other words, where y is equal to negative 1. Now, because we want to avoid the issue of having a hole in our derivative, which would indicate it's not a vertical tangent, the top can't be 0, right? So y is equal to negative 1, and x is not equal to negative 1. Of course, we need the points, right? So in addition to the y coordinates, we also need the x coordinates. So we're going to plug y equals negative 1 into the original equation for the curve. So into our curve equation. Okay, so we have x squared plus 2x plus, what was it, y to the 4th? So plus negative 1 to the 4th plus 4y, or 4 times negative 1. And that's all equal to 5. So quick little math here. We get what? 1 minus 4 equals 5. Add 4. Okay. All right, we just manipulate a little bit, do some algebra. We got what? X plus 2. X minus 4. Right? Yeah. Oh, no, other way around. Sorry. X plus 4. X minus 2. So two solutions. We have 2 and negative 4. That means that we're going to have vertical tangents at the points 2, negative 1, and negative 4, negative 1. Cool. One more part. Part D. Oops. Is it possible for this curve to have horizontal tangents at points where it intersects the x-axis? Ooh, tricky. So think about how you would go about solving that. I'm going to copy and paste this down here. Okay. So in order to have a horizontal tangent, right, we're going to have a horizontal tangent when the top of this fraction that is our derivative is equal to 0. So in other words, when x plus 1 equals 0 or x equals negative 1. Okay. Now, in order to intersect the axis, we would also need y to be equal to 0. We don't know if this point, negative 1, 0, is on the curve. So in order to test it, we're going to plug it into the original equation for the curve. So let's plug in negative 1, 0. Let's see if this is equal to 5. I don't think it is. So we get what? 1 minus 2. That's not equal to 5, right? So because we got something that was not true, that means that this point, therefore, negative 1, 0 is not on the curve. So it cannot have a horizontal tangent at, let's see, cannot have a horizontal tangent at negative 1, 0. Yeah. That's it. All right, moving on. Number 3. So we're doing a little graph analysis here, and I think I might have been a little ambitious with this problem considering we haven't had that much exposure to this content before the test. So I'm going to kind of tone down this question on the exam, or this version of our exam question. So let's see. We have a graph. This is the graph of f prime, the derivative. Okay. So the y values on this graph tell us the slopes of f. Keep that in mind. Part A. I want to find all values where I attain a relative minimum. Okay. Where f attains a relative minimum. So remember, a relative minimum is going to be some sort of turning point that's like the bottom of a valley, right? So we're going to have a relative minimum when the derivative, the slope, goes from negative to positive. Okay, where does this occur? In this problem, let's see, we go from negative to positive right here at -1. So this happens at x equals -1. When it comes to justifying our answer, we did the justification by kind of restating the definition of a relative minimum. So if we can state that and say this is where the criteria is met, we've justified our answer. Okay, so part B, same idea, except this time we're finding a relative max. So again, I'm going to lead with the justification. So we have a relative max when f prime of x goes from this time positive to negative, because we're looking for somewhere where the curve is going up, then it changes direction and goes down. Okay, well, where does this occur? Where do we go from positive to negative? Well, it looks like that happens at x equals -5. Okay, in part C, find all values where the second derivative is less than 0. Okay, so think about this. The derivative tells you slope. So that means f double prime is equal to the slope of f prime. Therefore, we know that the second derivative is negative wherever f prime of x has a negative slope, or wherever that graph is decreasing. Okay, so look, we have some intervals here where we're decreasing. Right? Anywhere else? No, I think that's our only places, right? Oh, I guess since we have a vertical tangent at 3, we have to think of this as 2 separate intervals. So like 2 to 3, and then 3 to 5. Okay, so f double prime less than 0 where f prime of x is decreasing, and this occurs on the intervals, let's see, from -7 to -3, then from 2 to 3. Because we have this vertical tangent here, we got to exclude 3 from that interval. So we break up 2 to 5, say from 2 to 3 and 3 to 5. Cool. And we're going to skip D again because we kind of only just really got into this material last week. So we don't have to worry too much about part D yet. All right, one more. So here, calculator section question, we're told f is twice differentiable. Okay, so we can take the derivative of f prime if we want. All we know about the original function is f of 0 equals 4. So we know we have this point 0, 4. Okay, we're given the derivative of f here. So right off the bat, the first thing I'm going to do is in my calculator, I'm going to put this function into y1. So let me go ahead and do that. Oh, minus 2x. Okay, so we need to know where this has a critical point. All right. Um, when we're looking for critical points, we're looking for where the derivative is 0 or undefined. Okay. Now, in the interval from -2 to 2, we shouldn't have anywhere where the derivative is undefined. It's a trig function. You can plug whatever you want into sine. So we're just looking for wherever this is 0. What I'm going to do is I'm going to look at the graph, super gross, go to your window. We only really need to look from -2 to 2. So I'm going to make my window just bigger than that. So -3 to 3. And we don't need all this empty space vertically either. So let's change this too. That looks a little nicer. All right. So from -2 to 2, it looks like we have what, 1, 2, 3 candidates. Right? 1. Yeah, 1, 2, 3. Second trace, 0. Right? Do the left bound, do the right bound stuff. I don't need to show you that. You know how to do that. So I did that earlier. And these are the x values that I got. So I got it was equal to 0 at let's see, I got -1.507, -0.772, and exactly 1. Okay. Now, if you look at the graph, you see how at 1, here, let's hit trace. We don't change signs, right? So it's a critical point, but because we don't change signs, it's not going to be relative extrema. The other 2 points, they change, the derivative changes signs there. So those are going to be relative extrema. Okay. So we're going to exclude 1 from, which one is the relative min, which one's the relative max. Okay. So because 1 doesn't change, or because f prime doesn't change signs at 1, we're going to ignore it. So we have a relative max at -1.507. And we're going to say because f prime goes positive to negative. And then if we look at -0.7, the derivative goes from negative to positive, so must be a relative min. And I'm writing shorthand here just to kind of save some space. So again, looking at the graph, you have, let's second trace. Oops. So at -1.5-ish, we're going from plus to minus, right? So that's a max. At -0.7-ish, right? There we go. We're going from minus to plus. So that's where my relative min lies. Cool. Part B. So in part B, what are we asked? Oops, I need to get this out of here. There we go. In part B, we're asked to find, use the line tangent to the graph to approximate f of 0.25. So that's that linear approximation stuff. So I'm going to kind of rewrite this. Right? We know that f of 0 equals 4. So that gives us our x1 is 0. Our y1 is 4. Okay. Our slope in this case is going to be f prime of 0. Okay, so f prime of 0. We actually don't really need a calculator to do this part yet, because if we plug 0 in for x, everything cancels except the 1. So sine of 1. So this is a gross decimal. I'm going to leave it as sine of 1 for now. So here's my tangent line. I'm going to say y minus 4 equals sine of 1 x minus 0. And we can clean this up a little bit. We'll say y equals sine of 1 times x plus 4. There's our tangent line. We're going to use this to approximate f of 0.25. So it's approximately sine of 1 times 0.25 plus 4. Let's pop that in the calculator, see what we get. $4.210. Oops. Didn't show up in the calculator, did it? 4.210. Cool. And one more part C. So we're going to use the mean value theorem, and we're going to explain why the average rate of change cannot equal 1.25. Why the average rate of change cannot equal 1.25. Again, I'm going to copy and paste this one. That way we can look at it while we talk about it. Okay. So let's think about this. In order to use the mean value theorem, we have to show that the function is continuous and differentiable. So we know we know f is differentiable. F prime is differentiable, right? F prime of x is differentiable. How do we know that? Well, we know that because we're told the function is twice differentiable. So that means the second derivative exists. If the second derivative, so if f prime is differentiable, what that means is our function f must be continuous, okay? Because if f prime is continuous, or if f prime is differentiable, it's continuous, right? So f must also be continuous. So f is continuous on the closed interval from -2 to 2, right? So we're going to apply the mean value theorem to f from -2 to 2. Okay, so we know f, the derivative exists. We know f is continuous. Okay, so we can say, so by the mean value theorem, there exists a c in what the open interval from -2 to 2, such that f prime of c is equal to the average rate of change of f on the closed interval. Okay. However, this is where it gets a little funky. Think about the fact that the derivative is a trig function. Sine of x squared minus 2x plus 1. What's the output of sine? What's the range of sine? The range of a sine function is -1 to 1, right? Therefore, we can say the range of the derivative is -1 to 1, right? So because the derivative f prime stays in between -1 and 1, that tells us that there's no way the average rate of change, right, could be equal to 1.25 because the derivative has to stay in between -1 and 1. Therefore, the average rate of change cannot be equal to 1.25.